Hey guys, welcome back to another video in this series on weekly paper reviews. So let's jump into it directly. The big news this week has been the Llama 3 model. I will jump into this paper, but before that, the other paper that I wanted to discuss is one is the Llama 3, and also this quite interesting paper on the scaling laws of vocabulary. And I will come to it in a bit once we discuss the Llama. So basically, the new family of Llama models was released, the 3.1 family, which has a 405 billion parameter model. So that's the big thing. I'm not sure if all of this is I mean, are they calling the 400 billion the 3.1, or um, there are separate 8p versions of? Oh, it looks like 3.1 is just an update of 8p as well. Okay, in any case, let's jump into the paper that came out. So the paper is interesting because it delves a bit onto the training strategy. So what these guys use is, so they've trained it up to have a context window of 128k tokens, which is good, but it's not the best. Like I've heard like Google or Gemma models, not Gemma, the Gemini models have a million, so this seems low. And let's see if this is multimodal or not. Oh, so they probably have some extensions to make it multimodal. And they have some initial results, so okay, not multimodal at this point. Yeah, so this is the interesting thing. They lay out all the different versions. Okay, so 3 is different and 3.1 is different. They talk about how if it's fine-tuned, multilingual, long context, trained on API calling, and so on. Most of it is standard stuff, and the cool thing is they show in the benchmark that how compared to the best model out there, which is 3.5 Sonnet, it wins in some, it loses in some, so it's quite competitive. And that's the good news, right? So you have an open weight model with architecture you can see. You have some details about how it was trained, beating these closed source models, or at least at par. So that's fantastic news. Okay, so what they've done, basically they did the standard pre-training that all LLMs do, and then they do fine-tuning and some DPO that also now all LLMs undergo. Right. So for the multimodal aspect, they have some other extra training. Basically, you need to align your language model with the new modalities, and also you need to adapt, perform the vision adapter training, and so on. So there are some details there. Yeah, this is the most interesting part to me. It looks like in the 3.1 400 billion parameter model has been trained on 16 trillion tokens. And compared to the previous versions of the Llama model, they have invested a lot in cleaning the data, making it much higher quality, which is what they talk about here in all the pre-processing steps that they do, all the document level deduplication steps that they do to clean the data, which is one thing. Then like how much of the data to use is the other thing. So finally, basically they train smaller models. They perform scaling law experiments on smaller models to identify the best data mix. And what they find is that half the tokens correspond to general knowledge, like the half of your training data set consists of general knowledge, 25% maths, and 17 code, and 8% the multilingual stuff. And what they do is they do some annealing on small amount of this code in mathematical to the data that to boost the performance of the standard pre-train on the different benchmarks. The architecture remains the same. It uses GQA, which is group query attention. They have an attention mask, like a large, like, so you have your causal attention mask, but they have this attention mask at a document level. So if you're feeding like two documents at the same time, because you have such a large window, you don't want the second document to attend to the first document. So that's what they're talking about. They have some attention mask, which is at a document level. They have a increased vocabulary. So Llama 3 has an increased vocabulary, which is 128K. We'll talk about this part later in the next paper, which talks about how larger models need larger vocabulary. So we'll delve into that. And then they have the base frequency of rope changed. So okay, so now they have this model which is this big. So how do you identify what is the data set you should train on? So they have, based on how many GPUs they have, how much time they have, they've come up with a compute budget of, so this is the number of flops they have. So how do we identify the amount of data that we should train on the number of tokens? For this, they do is run a bunch of scaling experiments. Like on their hardware setup, they for the different flop ranges, they set up models ranging from 40 million to 16 billion, and they would do pre-training rather, on all of these to get these curves. So these are called the isoflop curves. What they mean here is these are the training tokens. Each curve is on a standard compute budget. So each curve has a fixed compute budget, and this is the validation loss. And the idea is that they are trying to find, for a given compute, where does the minimum lie? For a given compute value, the minimum is obviously at the center of this parabolic region. And so an interesting thing happens is, so there is the minima is at the center of this region. The curves tend to flatten out as the compute grows. So these are the two interesting things that they note, and they try to fit or try to identify the number of tokens they need to use to be compute optimal by fitting all these red dots, and they come up with this equation that which basically tells it for the number of flops, for the given flops that they have, they need to train this 402 billion parameter model on 16.55 trillion tokens. So that's the rough average. That's how they came up with this number. Okay, then the rest is like, I think that was the coolest part, in my opinion. Like how much data did they train on, and how much did they identify? How did they identify how much data to train on? Okay, so they use a lot of GPUs, 16,000 H100 GPUs, and there's some details about the network topology, but I think this is all standard stuff. The additional thing that they do is they have 4D parallelism. So what that means is they have your standard tensor parallelism, the pipeline parallelism, and data parallelism. In addition, they have this context parallelism. The way I understand it is it just splits your prompt into multiple contexts, and each chunk is treated separately. And that's about it. So basically that's the only new thing, this context parallelism. And I think it might be easier to explain in this diagram. So okay, so let's say you have how many GPUs? Like 16 GPUs. This is how the model is split. So you have two instances of the model model 1 and model 2. So that means my data parallelism is 2. Then each model I split it into two parts. This is one part, this is the other part. So my pipeline parallelism is also 2. So again, same thing for the second model. Then the layers I split into 2 GPUs, which becomes tensor parallelism. And then context is split into, again, 2 sets of GPUs. So that's the context parallelism is again 2. So let's say you first feed in the first half of the prompt, and then it outputs. All the activations are then used by the second half. So this kind of works in that pipeline parallelism way, where this needs to do the computation first, all the activations then get ported over, and then this does all the forward pass on its part of the context. I think that's how it works. So that's the only new thing. Yeah, then it's a bunch of things about results and you know, how many training steps and what else do they do? They do a bit of DPO. They do so they do some SFT at the end to align them to do some instruction teaching on instruction alignment, and then they also do DPO to generate this like kind of chat model. So that's pretty much, and some amount of model averaging as well. Like when you have like different versions of DPO model, you can just average the weights. But those are all the major things that I kind of wanted to discuss in this this paper. But yeah, it's a large one, so go have a read if that interests you. That was about Llama 3.1. Now, we talked about the scaling laws. So this was an interesting paper that came out, and it suggests that hey, there's one axis which we kind of ignore in scaling laws, which is the vocabulary size. And what this paper argues that we shouldn't look at the vocabulary directly as a. So what is vocabulary? Vocabulary is basically your embedding matrix, because your embedding matrix, it would be your vocabulary size times the hidden dimension, and also that is your output if you have weights tied. So what they say is like these parameters, because they are inherently tied with your tokenizer and also the representation of the input, should be looked at differently. And what they argue is for larger models, you need larger vocabularies. So a 70 billion parameter model should need at least 216K vocabulary size. And this is how they, this is the scaling law equation that they get, that the optimum one is proportional to, so it follows a scaling law behavior. And then this factor will be measured empirically. Yeah, so this paper basically begins with reviewing like what the scaling laws are. So for a model, if you want to find out the optimum size of the model and optimal data set, you minimize the loss, the standard loss for that n and d, such that flops remain constant. So every time you're keeping the flops as constant. So you always know your compute budget, you know what GPU is using, you know how much time you need, and that's always fixed. And that's how the scaling laws were always derived. So here they argue that the number of parameters needs to be broken down in the non-vocabulary and the vocabulary ones. The vocabulary ones are the hidden dimensions, which is, like I said, the vocabulary size times the input dimension. So yeah, so they do a bunch of empirical analysis, compute, the same kind of like train multiple models, and finally what they find is let's directly go to somewhere. I guess they basically have 3 approaches of identifying the formula, and basically yeah, find that this delta factor is 0.83, some relation. Now when they put numbers, so this is the interesting thing, for the different models that are around, it tells you what is the vocabulary size and what should be the optimum one. Let me see if I can find a better table. It's flops is always a function that is always important in these things. So this is the vocabulary size. Unfortunately, this is in terms of this megabytes it occupies, which is weird. I wish. So yeah, vocabulary parameters. So as you can see, most of the models are not you. They're not making optimal use of the vocabulary. The current sizes of vocabulary are always maybe an order of magnitude or like half of that behind. So for Llama 2, it is terrible, behind what the optimal should be. So yeah, so that's so I think I found this paper quite interesting. Obviously I haven't taken a deeper dive, but I think at a high level, they suggest that with larger models you need larger vocabularies for optimal training or optimal performance as well. So that's pretty much it for this video. Yeah, like and subscribe, and thanks for watching. See you next time.